Hi, hello, and welcome. This is Greg Jacobs. I teach at Woodbury Forest School in Central Virginia. It's a boys' boarding school, and there are no boys here. The campus is empty and lonely, but I am really happy that we have a community of physicists here. It is great to have you all back with me today when we are going to talk about Newton's second law for rotation. Let's start, though, by talking about exam preparation. We don't know when the exam will be. We don't know the format. That will all be announced on April 3rd. But you might be asking, how can I prepare for the exam then if I don't know what's going on? Well, we know the general topics, but I would encourage you not to be thinking about, well, what topic do I need to do more problems on? We'll get there. I would encourage you to start with facts. Start with learning the facts of physics. And in the show notes, eventually, there will be a link to a blog post with all of the facts of physics on them. Pick a topic that you need to work on and then start with learning the underlying facts. And once you know those, then you can work more in-depth problems. So how do you know which topics to start with? Well, I would invite the exam fairy into your life. The exam fairy, well, she's not real, but imagine that she were. You say, exam fairy, and the exam fairy says, yes, I grant you 2 boons. The first boon is the exam fairy offers that if there is one topic that you really want on the exam, imagine that it's problem 1 and it's something that you know how to do real well. What would that topic be? Think for a moment. Whatever that topic is, you don't need to study that. Just go over the facts, you're done. Now, you can help somebody out with that topic if you'd like. That would be good community building, and you might find out something else that you don't understand real well. But if there's a topic that you're telling the exam fairy to put that on the exam as problem number 1, ignore it. You're good. You're good. You don't need to keep practicing that. But the exam fairy offers you a second boon. That second boon is name a topic, and the exam fairy will say, nope, it's not going to be on the exam. Okay, name that topic. Tell the exam fairy. Okay, now that's the topic you need to focus on because it's going to be there somewhere, somehow. We can't predict anything about what topics are going to be there other than that all the topics that we covered, except for circuits, electricity, and waves, will be on this exam. So whatever topic you ask the exam fairy not to put on the exam, that's what we need to focus on. Learn the facts and then do some problems based on those. And eventually we'll be able to see the published schedule of all topics that we're going to review. Josh and I will help you out with those. You can get a community of physicists. Go to @JacobsPhysics and you can start asking questions of me, of other people, and we will help you out. What's going to happen today? I'm going to do some screen sharing here so you can see a little better. This is our plan for today. We're going to go into the review question from Friday right now. I do point out again and again that if you have questions for me, go to Jacobs Physics on Twitter, ask them, and toward the end of the show, I will just go through and start answering your questions. Let's scroll down here. This was the question that we had from the other day. We have a disk rotating counterclockwise, and you can see in the corner of the screen, I'm just showing you that this is the same setup that we had the other day. The disk is rotating counterclockwise, and then we want to know what happens on a velocity time graph. Well, we know that we called counterclockwise positive, so we need a positive vertical axis value at the beginning. That takes away A. Has to be B, C, or D. Now, in the corner of the screen, you can see me pushing this up, and then this comes right back down. We know that the torques are unbalanced here. We'll talk about what that means in a few minutes, but we know that just doing the thought experiment, watching what happens, we know that eventually this disk is going to slow down and turn around the other way. Slowing down is indicated by the vertical axis value getting closer to 0. So that takes out B. Choice B, the vertical axis value stays the same. Choice C, the vertical axis value gets closer to 0. Choice D, the vertical axis value gets closer to 0. But when this disk flows to a stop and starts rotating again, the disk is rotating in the other direction, the clockwise direction. How do we find the direction of motion from a velocity time graph? We look at the vertical axis, whether that's above or below the horizontal axis. So we need the vertical axis values to go from up here to down here. Therefore, C is the correct answer. All right, is it the correct answer? You should never, ever, ever assume, that the answer is the answer. The teacher is not the authority. The universe is the authority. So let's do the experiment. Here is an angular velocity versus time graph, and I'm going to start it and do exactly what I showed you. Oh, look at that. Vertical axis value gets closer to 0 and then farther from 0 on the other side of the axis because the disk was rotating in the other direction. Isn't that nice? Now, let's move on to today's topic, Newton's second law for rotation. Newton's second law for rotation tells us that the angular acceleration is determined by two properties of the thing that's rotating. One is the net torque on the thing that's rotating. The other is the rotational inertia I. I'll worry about rotational inertia in a moment. Suffice it to say that that has to do with how much mass is rotating. We'll get to that in a moment. So let's imagine that I keep this same disk rotating. I don't change its mass. I can't change the rotational inertia. But I want to change the net torque. What's causing the net torque here? Well, the net torque is caused by the imbalance in the torques provided to this disk. Each of these ropes is pulling down the same distance from the axis of rotation, but they're pulling down with different forces. So the farther apart these forces are, the more unbalanced the torques are going to be, and the bigger the net torque will be. So now, instead of just this here, I'll do one more time. I'll let you see this one more time. I've changed this now so that you can see the vertical axis value increasing. I can check and see the slope of this graph. You probably can't read that, but it says about 7 radians per second is the slope of this velocity time graph. That means the angular acceleration was something like 7 radians per second. But now, let me put on a much bigger difference in these torques, a much bigger net torque. And I'm going to record this again, but this time I'm going to let you watch live because you're not going to need to see the velocity versus time graph to know what happened to the angular acceleration. You're going to be able to see it right here live. What is angular acceleration? Angular acceleration is the change in angular speed every second. Well, watch how much the angular speed changed more every second in this new case. Angular speed changed much more, which means we have a much bigger slope on this angular velocity versus time graph. That's this one right here. And I can actually check it. That's 40 radians per second this time, as compared to, in the previous case, only 7 radians per second. What happened mathematically from Newton's second law for rotation? We kept the same rotational inertia. We increased the net torque, which meant that the angular acceleration increased, and it did. We saw that for real. All right, let's go back to what we just had set up here. And we have a lot of net torque, big imbalance in torque here. I'm going to do this again, but now I'm going to keep this net torque the same. I'm not going to change what these masses are. Instead, I'm going to increase the rotational inertia, and I'm going to tell you what that means right now. Mathematically, that means the angular acceleration should be less. All right, well, let's take one more step toward our understanding of what rotational inertia is. Rotational inertia is going to be the resistance to the change in angular speed. And we can get an idea that if I have more mass rotating, then the rotational inertia is larger. I have a big disk here, big heavy disk. I'm going to put that on there. Get on there. There we go. I wanted Edna to help me out here, but she said she was busy. She's going to be featured later in the show today. Here we go. I have more mass rotating now. That means that the resistance to angular acceleration is larger. The rotational inertia is larger. And therefore, with the same net torque, we should have a smaller angular acceleration, leading to a shallower line on our angular velocity versus time graph. Well, I'm going to do it for you, but once again, you can just see that the angular acceleration is going to change less every second than it did before. The angular speed is going to change less every second than it did before. You ready? Let's show you the picture. This is the graph. The slope of the graph is now 22 radians per second. And compared to last time, you see last time we had the big green line that was very steep. This time we had the blue line. Physics works. Isn't that amazing? All right, we're going to get a little better understanding of what this rotational inertia thing is in a few minutes. Right now, I want to come up with a different way of creating a spinny thing and measuring angular velocity versus time. We've used a rotational motion probe. We got that. But what else could we do? I've got this platform over here. I'm going to spin this platform. I can spin this platform any way I want, and it just keeps going because this is a pretty darn low friction platform where it just keeps rotating at a constant angular speed. So I want to measure its angular speed as a function of time. I don't know how to do that right away. I can't just stick this rotary motion probe on there. That's not going to work. I got to come up with a different way of measuring this. This is good experimental technique. Like we talked about on Friday, we want to have an idea of what equipment is available in a typical high school physics lab. What can we use to make these measurements? Well, I've got this thing. It's called a photogate. This photogate, you probably can't see inside here, but you can see what its shape is. There are 2 holes on this side and 2 more holes on this side. Each hole houses an infrared laser. That's a laser we can't see. It's below the frequencies that our eyes can process. But there's a photoreceptor over here. So every time that this photogate is blocked, this thing knows. And it can tell very precisely how much time each of these lasers is blocked for. And these lasers are separated by 2 centimeters. So to find an instantaneous velocity, my program here can just find out what's the time it takes for these lasers to be blocked. I have a little flag here that's going to block each of these lasers in turn. And from the time between those lasers being blocked, this computer program can calculate the instantaneous speed. Then we can do that once, twice, a third time, and keep plotting those instantaneous speeds versus time. And voila, we have a velocity versus time graph. That's a linear velocity versus time graph. The conversion to angular velocity versus time will give us the same shape of the graph, but I'm going to let Josh tomorrow talk about the mathematical relationship between linear and angular velocity. So let's go to here. New setup here. I want you to see what I'm doing. I'm going to a different program, and I am connecting my new device, which should be my photogate. There it is. Edna hippopotamus. She is not a pickle. Edna hippopotamus. All right, it's working. What I'm doing is I'm putting my finger through back and forth in different directions, so it plots these velocities. Good. Let's stop that. Now, I've got this flag just as I showed you. I'm going to let this thing rotate at a constant speed, and I'm going to hit collect. And you can see it happening there, and you can see it happening live. If I start again, let this thing have a constant angular speed, and this time I'm going to give it a little frictional torque. You see this slowed down, so think what the angular velocity versus time graph should have looked like. Vertical axis was the same value for a while, and then all of a sudden, the vertical axis value got smaller. So I don't know why it's taking this slope. I don't want it to take that slope. There we go. That's what we wanted. Okay, so why am I doing that? Hello, there we go, we're back. I'm now going to apply a net torque to this thing. Underneath, there is a pulley system, and I've got a string attached to a massive object here. I'm going to wrap this string around my pulley, and then I'm going to put this over top of another pulley right here. And I'm going to move all this into position, put this back on top, move my pulley up. There we go. So now this hanging object is going to pull down and speed this puppy up rotationally. And then when the object gets to the bottom, the coil is going to unwind the other way and slow down this rotational platform. I'm going to make a velocity time graph, an angular velocity time graph of this rotational platform as a function of time. Velocity is a function of time. Every time that this flag passes through the photo gate, we get a new velocity. All right, are we ready? I'm going to let you see this develop. Here it goes. Angular velocity increasing as a function of time. And then when that thing bounces at the bottom, the angular velocity decreases as a function of time. Why did this happen in terms of net torque equals I alpha? Because for a constant angular acceleration, for a constant rotational inertia, we had a net torque that was non-zero. Therefore, we should have an angular acceleration. As long as there was a net torque, there's an angular acceleration. The net torque was provided by the string there. Let's look. Ooh, we are live. Let's look at this graph and see how it's sloped. I do want to find the slope of this graph. And I know you can't see that, but I'm going to read it to you. That's 8 centimeters per second per second. So now going back to net torque equals I alpha, I want to, this time, again, keep the net torque constant, increase the rotational inertia, and decrease the angular acceleration in this new experiment. How am I going to do that? Well, I could replace this rotating thing with a more massive rotating thing. Great, we've already done that. I did that for you on the other thing. Let's do something a little more interesting. Let's talk about the rotational inertia for a point object. What do I mean by a point object? I mean, if I put just like a very small coin on the edge, what would be the rotational inertia now? Rotational inertias are additive, so that means the total rotational inertia would be the rotational inertia of this rotating disk plus the rotational inertia of that point object. The rotational inertia of the point object is given by this formula. The mass of the point object times the distance from the axis of rotation squared. If I place that coin at the edge of this disk, well, that axis of rotation distance is about 12 centimeters. If I place this coin right in the middle, then that axis of rotation distance is very small, and we get a very small rotational inertia for the coin. How do I demonstrate this to my class? What does this mean physically? Rotational inertia is the resistance to the change in angular velocity, which means that something with a small rotational inertia can change its rotational speed more rapidly. I decide that we're going to have a sword fight. I have here 2 meter sticks. Each meter stick has a mass of 70 grams by itself. Each meter stick is attached to a 200-gram object here or here. I have the students come up and we're going to have a stage sword fight. And I say, choose your weapon. Think about which one you want to choose. Since I don't have a student here, unfortunately, who can choose their weapon, I'm going to roll a die. 1 through 5 is this one. 6 through 10 is this one. It's 7. So I'm going to use this one. Tell the student to hold it like this. I hold mine like this. This student's rotational inertia is the rotational inertia of the meter stick plus mr squared for the point mass. That's 200 grams times 1 meter, or 50 centimeters, sorry, half a meter. So they have to rotate the thing like this. But I am holding this right here, so that the 200-gram object has an R term that's close to 0. So the 200-gram object doesn't affect the rotational inertia, and I can swing this very rapidly. So I offer a stage sword fight, which is all about clashing of swords, and I just destroy the person. Nobody's ever been hurt doing this. I just want to make that clear. And I'll give you a trick of the trade. What if the student had chosen this one instead? Or what if the student had chosen this other one? I would have had the student hold it like this. Now it's got an even bigger rotational inertia because the R is 100 centimeters. And I would have held mine like this. Just so you know, didn't matter which one you chose, I would have won. So now we understand what the rotational inertia of a point mass means. We can put a point mass on the end here. We can increase the rotational inertia by placing a point object on the edge, and that will decrease the angular acceleration from the 8 centimeters per second that we had before to something smaller. Yes, I know that's a linear acceleration. Josh will tell you tomorrow how to convert that to an angular acceleration. Edna is going to be our point object. Edna loves this ride. I'm going to put her here. First, I'm going to wind this back up. I get sick on these kinds of rides. Edna does not. She loves them. Although on this one, she does have a tendency to fall off. So I'm going to be very careful to watch her and catch her. I'm going to collect on my screen here. You'll be able to see this in a moment. And then here we go. There we go. I caught Edna. And let's stop the collection and let's go look at what we have here. This is the vertical axis of the velocity time graph. Vertical axis value is getting farther away from 0. The slope of that gives me the acceleration. This is where I took Edna off. And let's find the tangent right there, 5 centimeters per second. So as we suspected, we went from 8 centimeters per second of linear acceleration of the edge of that flag on the edge to 5 centimeters per second. All right, last thing then. I want to, this time, decrease the rotational inertia in order to increase the angular acceleration from the 5 centimeters per second that we had of the flag just a moment ago. Come on, here we go. But I'm not going to add any other mass. I'm just going to have Edna. Edna's still going to be taking the ride. What do? Well, the rotational inertia of this whole device is the rotational inertia of the disk plus the rotational inertia of Edna about the central axis. Edna's mass isn't going to change. She's still the same hippopotamus she was before. But if I place her not at the edge, but close to the center, then I have reduced this R term, reducing the rotational inertia of Edna, and thus reducing the rotational inertia of the whole system. Let's try it. you can already, well, maybe you can't already see. I could already see it, but I've done this in rehearsal several times. So now let's, ooh, Edna, you okay? Yeah. My wife was saying we need to get Edna some bubble wrap or some kind of koozie or something like that to protect her while she's doing this experiment, but she's pretty sturdy hippopotamus. Let's take a look here. Slope, 7 radians per second per second. So just as we anticipated, the angular acceleration increased and we are in good shape. All right, let's go back to here. And that's what I have got for you today. Now, friends, is the time for questions. I'm going to my Jacob's Physics account on Twitter, and I am going to take a look in here and see all the various questions that are here. Ava, and I really am sorry about pronunciations. I want to thank Aldous Scary for this beautiful picture of what they think Edna looks like in their mind. I think that's wonderful. Thank you so much for the Edna fan art. It's going to be framed on my office wall. When I broadcast sports, the first thing I do is I go ask people how to pronounce their names. I can't do that here, but I saw Ava asking me. Ava says, how do you find rotational inertia of the system and not the point object? Rotational inertia is additive. The rotational inertia of the system is the rotational inertia of this disk plus the rotational inertia of Edna. We just add them together. The rotational inertia of this thing is the rotational inertia of the meter stick by itself plus the rotational inertia of the 200-gram object. And you say, but wait a second, how do you find the rotational inertia of this disk? Well, if we want to get into all those fancy formulas like 1/2 mr squared and 2/5 mr squared and such, well, we would have taken AP Physics C. We're not doing that. If you need a formula or a value, you'll be given that. All you need to know is that the rotational inertia of a system is additive of the objects in the system and that a point object has a rotational inertia of mr squared. Great question, Ava. Thank you. Happy Enderman says, can the formula for rotational inertia change with the, just went away, with the shape of the object? Yes, absolutely. Rotational inertia depends on two things, on mass and then on how far that mass is from the axis of rotation. That's why I could do my special little meter stick game. This is a hard sword to use because the mass is distributed far away. This is an easy sword to use because the mass is right at the axis of rotation. It's not just the mass, it's how that mass is distributed that indicates rotational inertia. That's as opposed to inertia in a normal situation. When I have a cart moving along a track, its inertia depends only on its mass. But rotational inertia, the resistance to angular acceleration, is determined by both the mass and how far that mass is from the axis of rotation. That's really actually a good question. Jay at Whoop Having Fun says they think that Edna is too thick to be a point mass. I know this person is having fun here, but that's a really good physics question to ask. Well, what is the boundary between a point mass that's like a teeny weeny coin and Edna, who's a big hippopotamus? Well, it all depends on the context of the problem. I showed you that assuming that Edna was a point mass managed to answer our question. When we decreased the R term, we decreased the rotational inertia and increased the angular acceleration. That worked. The universe told us that that worked. That's not just me telling you. The experiment did what we said it did. Therefore, that assumption was good. But at some point, if we get this really close, maybe that assumption doesn't work because Edna's too thick to really be on one side or the other of the axis of rotation. Well, at that point, that assumption doesn't work. Remember, an obsession with precision is our enemy in AP Physics 1. We make the most simple assumptions we can make. And then if they don't work, then we revise. In fact, that's not just Physics 1. That's how I teach my research physics class who are doing undergraduate level research problems. That's how I teach them to start. You might have a really freakishly complicated problem, but we always start with the most simple version of the problem we can. Assume the cow is a sphere. And then from there, we can make adjustments. We have more questions coming in here. Raj Jenkinson is asking, how do you find the rotational inertia of the disk by itself? We don't. That's either given in the problem, or we can just understand that for a disk, because rotational inertia depends on the mass and the distribution of mass, a wider disk has more rotational inertia and a heavier disk has more rotational inertia. That's all we got to know. We are not in physics C. If you want to go to graduate school mechanics, then you can really talk about rotational inertia tensors and some kind of crazy stuff. We're not there. Let's make it as simple as we can. Flooper Duper asks, yes, that is the actual name here, what determines the axis of rotation? That's a great question. If you have just a single disk rotating like this, well, the axis of rotation is obviously the axis about which this is rotating. When I had my meter stick, the axis of rotation is the axis about which this whole thing is rotating. But that's not always obvious. Sometimes we have to define the axis of rotation. If I throw this meter stick in the air, you see that didn't rotate like I expected it to. Take a hammer and toss the hammer in the air. That rotates in a really weird way. The axis of rotation you have to define. When you have an object that is rotating freely and doesn't have a pivot point, it's usually rotating about its center of mass. But if I stick this here on a pivot, well, then that axis of rotation is where that pivot is. Where the axis of rotation is depends on the context of the problem. Let's see here. Recycle Me has a brilliant question based on this particular setup. Recycle Me asks, how would you change the net torque to either increase or decrease the angular acceleration? I focused in this situation on changing the rotational inertia, but what if I wanted to keep that constant and increase or decrease the net torque? All right, I have to unwind this so you can see it. What's providing the net torque? Well, there's a string. There's a string attached to this mass. And to increase the net torque, I have to increase the tension in this string by hanging more mass here. I'll make it a huge difference so you can see. I'm going to go from 50 grams hanging here to 250 grams hanging here. 100. 250 grams. So the angular acceleration, since the torque just went way up, the angular acceleration should be huge. This thing should change its angular speed way more every second than it did a moment ago. You ready? Look at that. Look at how that thing's speeding up way more than it did before. That's because I increased the net torque without changing the rotational inertia. That is a great question. Oh, no. I didn't drop Edna, as Luna is saying. Edna jumped off. I know you've done this before when you were swinging as a kid and you just said, whee, I'm jumping off. Edna jumped off. And we've had a little talk about being careful because Edna is a little bit fragile. But yeah, well, we protected her. I knew that she was going to be okay because I did this before and she's done it before, and you have to let your hippopotamus be herself. Can I show the graph with Edna on the disk? I think that's this last one. Edna's on the disk twice. I don't know how to show two graphs at once, but in both cases, there, can you see that, I think? Nope, come on. There we go. In both cases, the angular acceleration was constant because the slope of this graph is constant. I don't think you're seeing it live now. Yeah, there we go, just as I press Control N. The vertical axis value is getting farther from zero. That means that the disk is speeding up. The difference was the slope of this graph was, the slope of the graph was shallower when Edna was on compared to when Edna was off. And we could find that by taking the slope. I have this button that just takes the slope for me. And that button said, with Edna off, said 8 centimeters per second. With Edna at the edge, that said 5 centimeters per second. And with Edna in the middle, it said 7 centimeters per second. Josh tomorrow will tell you how to convert that 7 centimeters per second at a 12 centimeter distance from the axis to an angular acceleration in radians per second. All right, one more question, and then we're going to go to tomorrow's problem here. Yeah, Brad Williams, thank you, Brad. He's been answering a lot of questions. A big shout out to all the physics teachers who are answering questions in the comments. But he pointed out the answer to the question of why was the graph above the horizontal axis in one case and below the horizontal axis in the other? Well, it just depends on which way this flag goes through the photogate. If we go through the photogate one way, the photogate considers that a positive velocity. If we go through the photogate the other way, it considers that a negative velocity. That's all there is to it. And finally, yes. Megan Alvord is answering this question, and I'm trying to see who asked it originally. The question is basically about, well, what do you mean common physics lab equipment? The problems in the AP exam usually say you have access to equipment that is available commonly in a high school laboratory. Well, that could be a lot of things because everybody's high school laboratory is different, as we talked about on Friday. But Claire's right that all that matters is that you talk about equipment that is real and that you show that you know how to use the equipment. You want to set up a photogate and a flag to find an instantaneous velocity of this platform. Sure, if you want to put this flag on top of Edna, like put her bow up like this and have her move along, and then set the photogate up so that the bow interrupts the photogate, well, that's going to get Edna's instantaneous velocity. But if you point the photogate at Edna as if it were a radar gun, it's not going to find Edna's velocity. On the other hand, a motion detector, do I have one in here? No, I don't have one here. A motion detector can find Edna's speed by standing back here, and it will send sound waves to Edna that'll bounce off of her, and you can make a velocity time graph of her that way. As long as you know how the equipment works, as long as you can explain briefly and draw a quick diagram of how you're using that equipment and what you're measuring with that equipment, it's good enough. You don't have to have the fancy electronic equipment. You can take a video and go frame by frame in the video with a ruler in the background. That will measure speeds. You can, I mean, you can do a lot of different things. You can use a stopwatch and your eyes and figure out how long it takes to go around once. And as long as the angular velocity is constant, that will get you an angular velocity by dividing 2 pi radians, 6 radians, by the time that it takes to go around. So there's a lot of different ways to make measurements, and it doesn't matter which one you use as long as you're clear. All right, time to share the problem for tomorrow. There we go. This is an AP style problem that I would suggest you solve tonight. Why would I suggest that? Well, because it's good practice, for one thing, on the topic of torque and angular acceleration, but also because it can lead into Josh Beck tomorrow talking about the relationship between angular velocity and linear velocity, which will include the relationship between angular distance and linear distance, between angular acceleration and linear acceleration. And you will understand after tomorrow's show why it is that I measured just a linear velocity in units of centimeters per second, and yet the graph of linear velocity versus time looked identical to what the graph of angular velocity versus time would look like. There is the rocket. That will be available if you go to the YouTube page later today. Well, you can always rewind and just look at that there. If you go to the YouTube page later today, my wonderful producer, Claire Lorenz, will post that file, including the link to the fact sheets. You can go download that. You can look at all those slides that I used today. She'll have those up. We also have those up from last Wednesday and last Friday. You can access those there. Yeah, I think that is all we need to do. I'm going to be on Twitter for another hour or so trying to answer people's questions. So please go at Jacobs Physics and you will be able to talk to me. I hope you'll tune in again tomorrow. Josh Beck is talking about linear and angular velocity. Wednesday, Josh will be talking about rotational kinetic energy. Until then, thanks for watching. We are on every weekday at noon. Say good night, Edna. Good night, everybody.